Okay, so this is a very typical work energy theorem problem. Okay, now, how do I know that this is a work energy theorem problem and not a Newton's second law problem? How can I tell the difference? In all the inclined plane problems we did during Newton's second law, how many times were you asked to calculate the speed at the bottom of the ramp? Never. Okay. Now that doesn't mean I wouldn't ask you to do that as like a part B after you've calculated the acceleration and everything, but it's not something I normally ask for. I also almost never give you the height, okay, or tell you how fast it's going at the top of the ramp. Like those are just not important for solving an inclined plane question. Okay, as a Newton's second law problem. So I give you a different data set when I'm looking for work energy theorem type problems. Okay, I'm giving you initial velocity, initial height, final height, things like that are very different from, I put a box on a ramp and the ramp's angled like this, calculate the acceleration. I give you a lot less, okay, for a Newton question. Okay, so we have this conveyor. All right, the first thing we want to do is diagram this because this is kind of our givens and it'll help us to figure out what we know. Okay, so we have a 200 kilogram crate and it's going to start right up here at the top of the ramp. Okay, the conveyor uses gravity by being angled at 15 degrees. Okay, so that's 15 degrees above from here, below from here. Does it really matter which one I write? It doesn't. It's similar triangles, right? So it doesn't really matter. Okay, and it allows the crates to roll down on the rollers. The crates are moving at 0.75 meters per second at the top of their ramp. So this is where they start, so that's their initial velocity. Okay, and they accelerate to the bottom, which is 2.5 meters below the top. So that means that my initial height is 2.5 meters. Okay, there is a frictional force of 150 newtons along the length of the conveyor. All right, if there wasn't any friction, this thing would just go right down the conveyor. Agreed? Okay, and it would just accelerate, and F parallel would be the only force and everything would be hunky-dory. Okay, but there is friction in this case. All right, so there's friction, and what is it going to do to the amount of energy the object has here compared to when it gets here? Okay, let me ask it a different way. Because there's friction involved and nobody's pushing the thing down the ramp, will it have more energy at the top or more energy at the bottom? More energy at the top. Okay? It's going to lose energy to friction as it goes down the ramp. That doesn't mean it isn't going to speed up. It's still going to accelerate down the ramp. There's no problem with that. But it's doing that because it's converting its potential energy into kinetic energy. But some of its potential energy is being converted into sound and heat and other things that are the result of friction. It's going to lose some of the mechanical energy it has here, so it will have less mechanical energy here. If I can recognize that from this picture, then I know that this is a work energy theorem problem where the mechanical energy of the box is going to change. Okay? Now, this is the part where I really have to see into the problem so I have all the information I need. Okay? Work is being done, and it's being done by what force? No, by what force? What force is changing the mechanical energy? We just said the mechanical energy at the top and the mechanical energy at the bottom are not the same. Why? What force is making them not the same? Friction. So that means friction is doing the work in this question. Okay? The force of friction is what's causing the change in energy. If there was no friction, the amount of energy this thing has here and the amount of energy it has here would be equal. Okay, everyone okay with that? Because there'd be no work being done. There'd be no energy lost. This thing would just fly down the ramp. Okay? All right, so we know that the force of friction is what's causing our mechanical energy change. There's a difference between the top of the ramp and the bottom of the ramp due to the force of friction acting over the length of the ramp. That's the other key thing. Friction doesn't act over 2.5 meters. It acts along this part of the ramp because that's where that force exists. If this thing just fell, there wouldn't be any friction, okay? And energy would be conserved and there'd be no work. But it is sliding down here and there is friction. So what do I need that I don't know? I don't know the distance over which the force of friction is acting. Can I find it? I sure can. I have the angle on the opposite side of that ramp, so I should be able to find how long the ramp is. Okay, so I've got to do that calculation. Okay, so D is the hypotenuse, so that'll mean 2.5 divided by the sine of 15. Okay, sorry, I skipped a step. Let me start again. I just saw like 3 confused looks as to where I got that, so I'll start again. The sine of 15 degrees equals the opposite side, which is 2.5, divided by the hypotenuse, which is D. Okay, so when I'm solving for D, I'm just cross-multiplying these two numbers, right? So D equals 2.5 divided by the sine of 15. So the ramp is 9.66 meters long. Okay, so now I've got D, right? So I can calculate the work already, can't I? I know the force of friction and I know the distance, so I can figure out how much energy is going to be lost from the top to the bottom. I don't really need that yet, but I can do it. Okay? So the next thing now is this part. The question wants to know how fast is the box going at the bottom of the ramp. Okay, so now I've got to work on the change in energy part because that's where I'll get that from. So I've got that the force of friction times the distance, and I know both those numbers, is equal to the final mechanical energy minus the initial mechanical energy. How do we calculate mechanical energy? An object's mechanical energy is the sum of its kinetic and potential energies. Okay, so I'm going to have then EK final plus EP final minus EK initial plus EP initial. Can I simplify that at all before I go any further? How, George?
You can do the the mass times gravity, and then initial height.
Oh, even before that. You're right, I am going to do that, but not yet. Right. How much potential energy do I have at the bottom of the ramp? Right. Okay, there's how I'm simplifying. I'm getting rid of one of them. Okay, don't bother having to write in a formula for that if it's 0. Okay. All right. So now I need to expand. Now I'm going to put in more stuff. So force of friction, okay, times distance equals EK final minus EK plus EP initial. All right. What I'm looking for is part of this, right? The final speed would be part of my final kinetic energy. So I need to isolate this. What should I do with this right now? If I want to get EKF by itself, what do I do with the stuff that's in brackets to move it? Add it to the other side. Okay, so here's what we're saying. Now that we're adding that to the other side, we're saying the work
plus the initial energy equals the final energy. That kind of makes sense. Work's a change in energy, so if I add the change in energy to the initial energy, I should get the final energy. Okay? All right, now I'm gonna make it bigger. Now I'm gonna put in the formulas for each one of these terms. Okay, so I've got force of friction times distance plus 1/2 times mass times initial speed squared plus mass times gravity times initial height. And that will equal 1/2 times the mass times the final speed squared. Okay, everybody with me so far? And this part's just algebra. We kind of did the hard intuitive part already. Okay? How do I get VF by itself? Right, divide both sides by 1/2 of m. And then what? Square root. Okay, now I can calculate VF. Okay, so I'm going to take force of friction, 150 newtons, times that 9.66 meters. Okay, so there's force times distance, plus 1/2 times, it was 200, right? 200 times 0.75 squared, that was my initial speed, plus 200 times 9.81 times 2.5, so my initial height, so there's my initial potential energy, okay? And then I'm going to divide all of that by 1/2 times 200, and then I'll square root it all. Okay, everybody with me so far? So 150 times our answer here. Okay, so friction is going to take away 1,448 newtons worth of energy between the top and the bottom. That's the amount of work friction's going to do. Okay, now I'm going to add to that my energy at the top. Okay, what do I have to make that number before I do that? It's negative. If I make that number positive, I'm going to say I have more energy at the bottom than I have at the top. I have to recognize that work done against friction represents a loss of energy or negative work. Okay, so I actually have to go negative answer. Okay, then add on the energy I had at the beginning. So that'll be my 0.5 times 200 times 0.75 squared plus 200 times 9.81 times 2.5. Okay, and then I'm going to divide that by 100 because that's half of 200. And now what do I do? Square root. Okay, so at the bottom of the ramp, it's going to be going 5.9 meters per second. Okay, so the intuitive parts of this question, okay, were figuring out that I needed to know friction acted over the long part of the ramp and not the height. Okay, figuring out that there was only kinetic at the bottom and both kinds at the top. Okay, and then realizing that friction worked against me and took energy away, so I had to make the work negative. Okay, those are the intuitive parts of that question. The parts that aren't about calculating something. Okay, that's just the stuff I have to know so that I can calculate stuff. Okay, that's what's tricky. Okay, you guys can do this math. It's not, okay? I know you guys are good at math. You can do that. That's no problem. Okay, it's the intuitive part that takes practice. All right, any other questions on that one? Okay. All right. we did, we looked at this, I think, already, right? Back in the other unit, or did we? Okay, perfect, because then we get to watch the video. Okay, all right. Anyone seen Raiders of the Lost Ark? Okay, if you're not holding up your hand right now, get a life, okay? You need to go home this weekend and watch Indiana Jones and the Raiders of the Lost Ark, okay? Well, it's too late now. Just go home and see it, okay? It's okay to tell me the truth and say you haven't seen it. It's a very old movie, okay? It was made in like 1982, all right? So it's like almost as old as me, all right? And Harrison Ford, he looks a lot younger, because he is a lot younger. Now he looks like a decrepit monkey skeleton, but okay, he's much, much older now, okay? And he breaks easily, okay? He breaks a lot more easily now. Back when he filmed this, he didn't break very easily. In fact, he did some of his own stunts, and one of them required him to be drugged behind a moving truck, okay? And his hat, you know, if you've seen Indiana Jones, his fedora is a big part of the costume. He never loses it. It kept blowing off, so he took a staple gun. And there's actually cut scenes of him in the extra features where he's stapling the hat to his head. Yeah. That's hardcore, man. Okay, that's method acting. I can't lose my hat. Okay. All right, so watch the video. Okay, so the big rock comes rolling down that big old ramp and then through the tunnel towards Indiana Jones, and he has to outrun it, okay? Obviously, there's potential energy at the beginning of that question, right? The rock perched high above everything else, okay? When it's released, it rolls down, and you can hear it. It's very loud, okay? And what does that mean there is? Friction, right? So it's losing some energy because work is being done against friction as it rolls through the tunnel, right? Eventually it reaches the end of the tunnel, okay? And at that point, all of its energy would have been converted from potential to kinetic. Okay, well, minus the stuff that's lost to friction along the way. Okay, so that's the type of question that we're dealing with here. So it's very similar to the crate question, just not quite as involved. Okay, we don't have to calculate angles or anything like that. Okay. So we know it rolls 30 meters against a frictional force of 800 newtons, okay, and it was moving at 4.5 meters per second when it slams shut the door on that temple, or whatever it was in, okay, so that's its final velocity is 4.5 meters per second, okay, and it's dropped. So we're trying to figure out how high it was dropped from, okay, so remember it only had potential at the beginning, it only has kinetic at the end. Work is done against friction along the way. Figure out that initial height from that. Let's have a look at this one. So essentially what we have, I mean, it's still a ramp. The rock is rolling downhill. We just don't have to treat it like a ramp. Okay? So we've got the rock at the beginning, we got the rock at the end, okay, and we know that the length of the ramp is 30 meters, okay? We're trying to find out how tall is the ramp, or the initial height of the rock, okay? What we do know here is that initially, it's stationary, okay? It isn't released until he puts the bag of sand to replace the giant lump of gold that he took, okay? And then that triggers it to fall. And then we know that at the bottom, the speed is 4.5 meters per second, okay? What's the height at the bottom? 0, okay? So we know that work is being done, because they told us there's friction here, and that that's going to change the mechanical energy of the rock. Okay, now we want to expand this out a little bit. The work is being done by friction. So that'll be force of friction times distance, and that force of friction will need to be negative so that I get a reduction in my mechanical energy. All right, that's going to equal my final mechanical energy minus my initial mechanical energy. Now, when I look at this situation, initially, I'm not moving, so I don't have any what? there's no kinetic energy initially, only potential, and vice versa at the bottom where I have no height and only speed. So I can say force of friction times distance equals the final kinetic, because that's all the mechanical it has, it's all kinetic at the bottom, minus the initial potential, because that's all it has at the top. Okay? The difference in those two numbers is the amount of energy lost to friction, or the work done against it, on the way down. Okay? All right, so now, what I want to find is part of the initial potential energy. Right now, I'm subtracting that number. Is that a problem? Yeah, because if I solve all this, I'm going to get a negative height, which means it started out in a hole and rolled uphill. Okay, which it definitely didn't do. All right, so what I'm going to do is just switch these two things here. I'm going to put my my initial potential over here and say that my initial energy equals my final energy minus the work. Which should make sense, right? My initial should be the final minus the change. Okay, so now, okay, I'm gonna put in my formulas here. Okay, I'm looking for m times g times h initial on this side. Okay, 1/2 mvf squared here minus force of friction times distance. All right, now if we're thinking this through logically, the force of friction times the distance is going to be a negative number. Okay, and I'm subtracting a negative, which really means I'm adding these two numbers, and that means this is bigger than this. Is that okay? It is. It's supposed to be. We're losing energy as we go down. We had more initial energy than final. Okay, so I'm trying to find just HI, so I want to divide both sides by m times g. All right, now I'm finding the initial height. This is more like what you'd get on a unit exam. Okay, it wouldn't give you one as involved as the conveyor question we just did a minute ago. Okay, this would be more like what we would do. So initial height is going to equal 1/2 times, what did we say the mass was, 400 kilograms?
Yep.
Yeah, okay. Times 400 times 4.5 squared minus 800 times, is it 30 meters? 30 meters. Divided by 400 times 9.81. So that should give me the initial height the rock was dropped from. Sorry, yeah, and this should be negative, yes, minus the negative 8. So 0.5 times 400 times 4.5 squared. So there's my final kinetic energy, plus 800 times 30. All right, and then divide that by 400 times 9.81. Okay, so it's dropped from a height of 7 meters, which kind of fits. I mean, when he first heard the rock starting to move, he went like this and looked way above his own head. Harrison Ford's about 2 meters tall. Okay, so when he did this, it was obviously way higher than he was. He was looking almost straight up. If it was dropped from a height of 3 meters, he would have just gone, oh, there it is, instead of looking way, way up. Okay, so kind of all fits. Okay, everyone kind of follow how we did that? All right, that one was quite a bit simpler than the conveyor question. All right. Anyone need that anymore? Okay, 14 we got. Okay, this is an important one to think about. I hold an object 2.2 meters above the floor for 10 seconds. Okay, so I'm doing this. How much work am I doing? None. Why? okay? It's not moving, so I'm not changing its energy, okay? It's not going higher or lower, its potential energy is remaining the same, it's not moving, so it's got no kinetic energy, there's no change in energy if I hold something still. You'd be surprised how often I get people on a multiple choice question with exactly the same situation. Okay? I say, this thing is held perfectly still. How much work is done? And they automatically go, m times g times h, and they figure out how much potential energy it has. I didn't ask how much work I did to lift it here. I asked, how much work am I doing right now, holding it here? None. Okay, I'm not doing any work to hold it because I'm not changing its energy at all. Okay. All right. Okay, see if you guys can do this one. There's two ways to do it. A short way and a slightly longer way. The quickest way to do this one is that work is a change in mechanical energy. Okay? What kind of energy is changing here? Just kinetic. It's not moving up or down. So really all I have is that the work is the final kinetic energy minus the initial kinetic energy, which is 0. All right, so all I have to do is go 1/2 times 10 times 11 squared, and I get my 605 joules. The longer way to do that is to calculate the acceleration, then multiply by the mass, and then multiply force times distance. I don't know why anyone would do it that way. That's 3 steps. This is 1 step. This is faster. Way faster. Do it faster. Okay. Have a good weekend. Good luck, football guys, tonight, and volleyball players if there are any.